So, hello, my name is Nirmal Raj. I am a faculty at the Center for High Energy Physics, and I'll be teaching the course, the NPTEL course, Particle Physics and the Standard Model. Okay, we'll see what these two phrases mean. This course is being taught at IISc. I taught this last year also, as nuclear and particle physics. Okay, same content. So, if you want to know the course number, so that you want to look up some resources, then it's HE or PH215. All right. So, just to dispel some misconceptions, when we say particle physics, you are probably thinking, if you did not know what the deal was about, you might probably have images like this, right. You might have some particle coming in, scattering on some particle at rest in some frame, scattering out, and then probably you have some particle traveling along, decaying to a couple of daughters, so you can call this chi and phi and so on, and you want to use kinematics. In particular, you want to use Einstein's relativistic equation, you want to use this formula in various guises to understand what is going on in the initial state and final state and so on, right. So, all of this constitutes particle physics, definitely. This is but only the kinematics part of it. Okay. This is probably what you are expecting about particle physics, right. But this course is going to look more like the following, all right. I am going to write down things like, the Lagrangian with stuff like the field strength tensor, all right, and then things like this, okay, and we are going to deal with symmetry. So, we are going to look at symmetry groups like this and so on, okay. So, we are going to approach particle physics more from a field theory point of view, okay. So, and you will see why, because that really is the approach that leads on to the relevant kinematics, the relevant particle processes, okay. This is the underlying code to understand what is going on stage here, okay. But do not worry, all the field theory that you do need for this course will be developed from the ground up right here in this course, all right. Any field theory that you need and any quantum mechanics that you need as well. You do need to know some quantum mechanics already. So, the course is also going to look a lot like, you are going to write things like this a lot, okay, just to prepare you mentally for what you are going to see in this course. All right, with that, let me move on to a rough outline of what the course is going to deal with. You would have already, you could already take a look at this in the modules that are being provided, in the syllabus that is being provided, but roughly speaking, here is the shape of the course, okay. So, first we will be dealing with the concept of symmetry, okay. So, let me write, let me first write, rough syllabus, the rough shape of the course. So, first symmetries, okay, and in particular we will deal with discrete symmetries, things like charge conjugation, parity, combinations of those, time reversal, combinations of those, and so on. All right, and how these dictate how the world looks. And we will also we will get an introduction to continuous symmetries, which you can further divide into global and local symmetries that underlie the world. And this is where we will also encounter group theory, which I will introduce. All right. So, group theory with various abelian, non-abelian groups and so on. Okay. And then once we have this at our disposal, we will use these principles to actually build or construct the standard model. Okay, just write SM. Standard model being the expression of these principles in the real world. Okay, the best microscopic theory that we have to describe the real world, right? So we will use these as ingredients, and we will put them to study the exact gauge interactions. Okay, and then what we will do is we will sort of deconstruct the standard model. What I mean by that is we will, so to speak, break the symmetries that we just talked about. Okay, it's a very specific term, breaking symmetries in various ways, spontaneously, dynamically, explicitly, and so on. Okay, and that's going to result in the particle menu that we see in laboratory experiments. Okay, the particle menu and their various interactions and so on. So to give an idea, this is where we are going to encounter, you know, things like neutrino oscillations, flavor changing neutral currents. So I'll just write flavor currents, flavor changing charge currents, neutral currents, etc., etc., etc. Okay, all these. Let me call it phenomenology. Okay, all these phenomena, right? So the study of phenomenology. Okay, that basically forms a lot of Nobel Prizes in the last few decades. Okay, and then once we understand these things, we will move on to particle processes. Okay, because it's these processes that give us a window into the underlying code of the universe, right? So the particle processes, we will for instance look at decays, various scatterings. Okay, so to give some examples, we'll deal with beta decay, muon decay, proton decay, and so on. We will scatter electrons and positrons to give us various lepton anti-lepton final states. We will do deep inelastic scattering and so on. Okay, so this should take up our 30 hours for this course. All right. So, all right. So without further ado, let's jump into some fundamentals of what we are going to be doing here. Okay, let's build up a picture for what we are really dealing with here in this course. Okay, since the course in both versions, in both the NPTEL and the IISc versions, since it has the word particle in it, it's about particle physics. Let's ask the question, what is even a particle? What is a particle actually? What is this particle that people talk about? Okay, any guesses? No wrong answers actually. You literally say there will be no wrong answers in the end.
It has mass and form of energy.
Okay, it has mass. Does it have to have a mass? Is a photon not a particle? Form of energy, okay. Could any form of energy be a particle? Could temperature is a form of energy. Like the entire ambient bath has some average kinetic energy. Would that be a particle?
Excitation of fields.
Excitation of fields. Good. That's where we are getting at. Okay, there's a very that's kind of almost a precise definition of what a particle is. Okay, it is a quantum excitation of a field in a very particular space called the Fock space. We won't get too much into it, but we will touch upon it. That is the sense in which we are going to deal with particles here. Okay. Okay. So is an atom a particle? Okay. It's made up of further particles. Is that allowed? Okay. Okay. So composite particles are also particles. You just have to call them composite particles. Good. Then let me ask, is this pen a particle?
Yes.
Okay. How come?
It's made up of atoms.
Yes.
Composition of atoms.
Okay. Okay. Very good. Very good. But why is it odd that a pen is a particle? When we say an atom is a particle, it doesn't feel so odd. But when we say a pen is a particle, yeah, technically it is. But why does it feel weird to call a pen a particle actually? Why did we have to laugh when we said a pen is a particle? Something was off, right? What happened there?
Its size.
But is it really the size? Then if it's the size, let me ask another question. Is a black hole a particle? Many people think, yeah, they can be just characterized as particles, right? They're characterized by their mass and spin and little else, right? So, and that's how we characterize a lot of quantum states anyway. So, okay. So, okay, let me ask in a different way. Could a galaxy ever be a particle? It can. It depends on the problem that you are dealing with. Okay, so if you want to simulate the universe, then you can treat galaxies as point particles for that particular problem, right? Now in this case, when we went from something that feels microscopic to us like an atom or a molecule or a nucleus, and then we scale it up to a pen, what has happened, the reason you put all these composites together and make a larger composite, and then it feels odd to call this classical looking object a particle, because what ultimately is going on is what's going on at the energy levels, right? In an atom, it's easy to actually visualize the discretization of the energy levels, right? Whereas for a pen, we do know, because we've eaten the quantum apple, we do know today that the energy levels of this pen are also discretized. It's just that the spacing is now so small, so narrow, that it behaves like a continuum, the correspondence principle, right? So it really depends on at what point you want to call it classical and what point you want to call it quantum. Okay, it comes down to that. the relative spacing between the energy levels compared to the total energy of the system itself. The spacing of the pen of the energy levels in the pen is much smaller than the total energy of the pen itself, the mass energy and possible kinetic energies and so on, the binding energy and so on, right? So So what we do call a particle and not a particle is indeed arbitrary, both in the quantum sense and in the sense of what problem that we are dealing with. Okay, anything could be treated as a particle given that problem. Now in this course, very specifically we are going to take particles, we are going to see particles in two different senses. Okay, one is as one of the students here said, it's an excitation of a quantum field. We will, these are just words at this moment, we will see exactly what this means, okay, in the duration of this course when we start introducing quantum field theory. What is even a quantum field, right? It's a very weird object, okay. And what is an excitation? It's not the excitations that we are really used to in quantum mechanics. This is a different kind of excitation, okay. That's one way to see it. Another would be, again I am going to throw some jargon out there, but we are going to see exactly what these words mean, okay. Another is, these are irreducible representations of the Lorentz, maybe even the Poincaré group. Okay, you are probably familiar with the Lorentz group or even the Poincaré group from special relativity, but you may not probably know what irreducible representations mean. That is a group theoretical concept, and this also we are going to encounter in great detail, okay, not to worry. So this is the sense in which we are going to deal with as deal a particle. I mean, this is how we are going to use the word particle in this course. Okay, excellent. Now in the last 10 or 15 minutes we have in this episode, let's talk a bit about what is particle physics now, okay. What is particle physics? Why do we want to do particle physics? Why do we even care about this course? Why do we even care about this field of study, okay. Now having spent so much time talking about what a particle is, let me tell you that particle physics is not about finding new particles, okay. In the news we see this, tetraquarks have been found, or some time back we saw the Higgs boson was found, the top quark was found, the world coalesced over it, and then we all took a lot of joy in it, celebrated it. But it's not really about finding new particles, okay. This is not a great specimen that we are collecting for our museum. No, that's not what's going on, okay. So let me write this down because it's important. So why particle physics? Not about finding new particles, or let me say particle species. It's not about finding new forces either, okay. Some of you may have seen that we've been discovering newer and newer forces, right. We used to know about gravity, then electromagnetism came, then electricity and magnetism came, and then they were unified into electromagnetism. Then the strong nuclear force came and the weak nuclear force came, right. And these are all very exciting developments, but it's not really about finding these whole new fundamental forces either, okay. The real pursuit of particle physics is to find new principles of physics, okay. So in that sense the word particle physics is a misnomer. Some people use the word high energy physics because to find newer principles you need to go to higher energies in the laboratory or in general, but I don't like that name either. I like the name, I know it's closer to fundamental physics, okay. Although in this course we will deal more with the phenomena of particles, all of this falls under the rubric of fundamental physics, okay, because we are finding more and more fundamental principles of physics. And what do we mean by principles? Well, new concepts, new theorems, okay, or organizing principles, new laws of physics. There are various ways in which you can these laws manifest themselves, and so on. Okay, so that really is the pursuit of fundamental or particle physics. It's about getting as few equations as possible, as few principles as possible, to explain a wide variety of seemingly disparate complicated phenomena. And this also goes by another name, right. This is the principle of reductionism, inaugurated by Isaac Newton himself, right, because he wanted to understand all of nature, and he was the first great unifier of physics, especially through his universal law of gravitation, by which he put together completely different looking phenomena like planets going around central stars, the moon going around the earth, and apples falling to the ground. He put all of these together into just one or two equations and explained all these phenomena with one minimal principle. So that's the sort of stuff that we are aiming to do here. Okay. All right. Now, having said that, perhaps the most important principle that we have learned to use in modern times to explain many phenomena is symmetry. Okay, how to use the concept of symmetry to understand physics, right? And this was begun by, any guess, who started identifying symmetries as the ultimate? No, before that. Good. Noether, yeah, she was probably one of the most important pioneers. But really, in my book, the person who started this was Einstein, right? So Einstein was the one who identified the Lorentz symmetry, and what came out of it, special relativity, and then later general relativity. These are very rich, gave rise to a lot of rich physics, right, as we know. Okay. So in the last 120 years, this is one of the main guiding principles in particle physics, okay, identifying newer and newer symmetries. All right. So let's look a little bit into what we mean by symmetries exactly. All right. So to illustrate, let's say we have an object, okay, going around the sun in some orbit. All right. What do you think the symmetry of this problem is? Rotational symmetry. Okay. How are you saying this? What is making you say this? Just tell me what, just think aloud. Okay, if both objects are round, then different points will seem the same. What if they are not round? What if, I just have two asteroids, one big asteroid, one small asteroid, let's say. And the smaller asteroid is somewhere in orbit around the larger asteroid. See, what I did not tell you here is, I didn't tell you the shape of the orbit here. I didn't say if it is a circular orbit or an elliptical orbit. I didn't even tell you if it's a hyperbolic orbit. So this need not even be actually a closed orbit, hyperbolic or parabolic orbit. But there is still some underlying symmetry here in the problem. And the answer is, it is still rotational symmetry. So how did that come about? Excellent, exactly. See, this is exactly what had tripped up people like Ptolemy and I think even Copernicus, okay? But exactly where Newton didn't go wrong. Because people like Ptolemy and Copernicus were looking for, or even Kepler, they were looking for symmetries in the picture itself. They were looking, they wanted elliptical or they wanted circular orbits. They put, shells, circles, etc., around the central object. But that's really not what you should be thinking about. You should be thinking about the symmetries in the equations governing the motion. Okay, so in this case, famously, so we have we have this, or which gives rise to the potential, which is actually a function of the magnitude, right? Right? This is the potential that's governing everything, whatever be the orbit, whatever be the physical picture, right? And this, you will agree, because of the presence of this object, which does not care about the direction in which you are pointing at, this is what gives the problem its rotational symmetry. That is, if I rotate the coordinates, then then the law is not going to change. The phenomenon is not going to change. I can do this in any coordinate I want under rotations. Okay, so just remember this. Okay, every time you get tripped up by what is the symmetry, remember this example. It's always about the symmetries in the equation. We'll see later that there will be the symmetries in the Lagrangian that we actually care about, which will also show up in most cases as symmetries in the equation of motion. Okay, not always. Sometimes the equation of motion has more symmetries than the actual Lagrangian symmetries, but I don't think we'll deal with this in this course. Okay, okay, very good. So I'm going to wrap up now for this half an hour module. Let me wrap up with the ingredients that we need to basically build a universe. Okay, maybe I'll just have time to do one thing here. So the main thing we're going to put in when we're going to use symmetries, the main principle that we're going to put in is Noether's theorem. Someone here mentioned Noether, right? Now again, if you are taking this course, you are probably familiar with Noether's theorem already in some form or the other. It's a theorem that states that for every continuous symmetry in the problem or in the equations governing the problem, there is some conserved quantity. There is an exact corresponding conserved quantity, right? So let me put it this way: symmetry in most cases continuous. There are some special cases where this works for discrete symmetry also, implies conserved charge. Okay, it's not really electric charge. Whatever is conserved, it is a Noether charge. Okay, so we'll use this term for the conserved quantity as far as this principle is concerned, right? So let's take some well-known examples. Suppose my system was invariant under this time translations, right? Then what is the Noether charge for this? Energy, exactly. Good. And suppose the system is invariant under spatial translations. Yeah, good. Okay. So let me redraw this. So I'm just going to write momentum, okay? It's understood as linear momentum. Okay. Now, what is this? Okay, good. So let's be very clear. Okay, good. So that's rotation, right? Under rotation, angular momentum. Good. Okay. So who knows this? I've taken a wave function or a field and rephased it by some quantity, and the phase itself is a function of coordinates. Rephasing a wave function or a field. If a theory is invariant under this, what is conserved? Is it current really, or?
Current density, probability density.
Okay, probability density. Okay, okay. Yeah, one could say that. If it's a field, what would you call it? So that's exactly charge. Okay, if this were the electron field and I rephase it, and the phase itself is a function of space-time coordinates, that's exactly electric charge. Okay, so we will encounter this more. So the last thing I'm going to write down in this class is, suppose what is this? What does this notation stand for? It's a Lorentz transformation. Good. I've transformed the entire 4 vector under boosts and rotations. You will see that the Lorentz group contains both boosts and rotations. What is conserved here? Have you encountered this? So the last time I taught this course also, this was exactly the answer I got. But think about it. Is space-time interval really the conserved quantity? It is an invariant quantity. Is it the conserved quantity? Under rotations, right, the length of the vector was also invariant, but it's not conserved. Conserved means as a function, it is constant as a function of time, right? No, it's not. No. 4 momentum is not conserved. That also transforms under Lorentz boosts, right? See, this is not something that you encounter, commonly. So I don't expect you to know the answer, but I would like you to go and look this up. Okay. The conserved quantity, as far as I know, doesn't really have a name, but it is there nevertheless. Okay. It is the position of the center of mass of the system. To be exact, it is this times the total mass of the system. Okay, you can first see this in Galilean transformations, right, for non-relativistic boosts, right? And then you can see that it's a more general quantity that you can write down for Lorentz transformations. In Galilean transformations, it is exactly the position of the center of mass. In Lorentz transformations, you cannot really call it that, but there is nothing else that you can describe it using English. Okay. The weird thing is, because the system could be moving in some frame, the position is actually a function of time, right. So that means although this quantity is conserved, it is time dependent. It's a bit weird. It's a function of time, but it's a constant as a function of time. That is, you differentiate this charge with respect to time, you still get 0. Okay, that is what it is. Or you still, it's still conserved. Sorry, you still get something that's constant. All right, so I think that's a nice place to wrap up. And in the next class, we'll explore consequences of symmetries some more. Okay, thank you.